Hello and welcome back. In this series, I'm walking you through how I built a custom physics package in Unity ECS. I called it Little Physics. In this video, I'm going to talk about a spatial map concept. Before we begin, please hit the like button and subscribe to this channel. Also, just a quick note that in the course of this series, I'll try not to go too deep into the Unity ECS concepts, but if you want me to talk more about it, let me know in the comments. Why do you need a spatial map? When calculating physical interactions between objects, you cannot simply compare every object against each other. That gives you O(n)² complexity, and as your object count grows, performance drops fast. The natural solution is a spatial map. You divide the world into a 3D grid of fixed size, and associate each object with the index of whatever cells it occupies. Then, instead of comparing everything against everything, you only compare objects that share a cell. With that in mind, the physics pipeline breaks down into 3 core steps: add objects to the map, read from each cell, calculate intersections between objects within the same cell. Each object participating in the physics pipeline has a physics body component. It contains physical properties and a collider shape and size. In my package, I work with 3 types of objects: dynamic objects, static objects, and triggers. Static objects don't move. They only added to the map once after they first appear on a scene. Dynamic objects added every frame. And for triggers, I added a special property called update interval, which tells the system how often to update trigger on a map. To store a map itself, ECS gives us a way to store large data structures in persistent memory. For now, we will use a native array with a persistent allocator, where we are going to store object indices. The catch is that native structures and dots are one-dimensional, but our spatial map is a 3-dimensional cube plus each cell containing multiple objects. Let's say it can be only 8 for now, which makes it a 4D structure. So we now have to do a bit of index math to convert 4D array into 1D and back. This leads to an obvious problem. Imagine a million entities all landing in the same cell. When designing a system like this, you face trade-offs. You could resize the map dynamically based on object's density, but that means recreating the entire structure in memory, which is expensive both in time and resources. Persistent data structures in ECS also continue to occupy memory even after being disposed of. To solve that, I set a hard cap on how many entities can be in one cell. That value then I use when creating arrays of maps. Also, the size of the map, cell size, and the map position are all predefined and are constant for the scene, as well as the maximum number of entities the system can handle. About that limit, I will talk more in the next videos. In the very start of the pipeline, we copy all physics body components into a flat array of physics body data. This keeps our component data and transforms isolated from the rest of the physics pipeline. We also set a hard cap on how many objects the system can process. Anything beyond that cap gets skipped. After that, we run a parallel job for writing objects into maps. Each job instance takes a single entity and calculates what cells it will occupy based on object's position, collider size, object scale, and object shape. It then writes the entity's index into the relevant cells. Now, if you want to support different shapes of colliders, here we face a slight inconvenience with ECS and data-oriented design. You can't really use interfaces or enumerator for generic iterations the usual way. What you can do is define a method that takes a ref to some iterator type and run a while loop around it, passing the iterator into the loop's condition. That gives you a form of polymorphism. If you want to support a new object shape, you just implement a new traversal method. There is another problem worth thinking through. Say your cell size is 1 unit. An object of a scale 1 occupies 1 cell. An object of a scale 2 occupies 8 cells, which is 2 multiplied by 2 multiplied by 2. Scale it up further, and the number of writes operations grows exponentially. To address this, I introduced a max cells per entity setting. When an object would occupy more cells than this limit allows, the traversal function skips cells pseudo-randomly, so coverage is still distributed across the object's volume. The trade-off that the system becomes slightly less deterministic. If that matters for your case, you can increase the property max cells per entity, but that will make a system slower and would require more space. Now a problem that some of you have already spotted. Write jobs run on parallel thread. If two threads try to write to the same cell at the same time, unpredictable things happen. Race conditions, corrupted data, or crashes. There is also a question of how thread knows how many objects are already in a given cell before writing. ECS does provide native parallel multi-hash map structure for this kind of scenario, but the problem is they block access to the entire array when writing to a single element. That's more than we need. When one thread is writing to one cell, all other cells should be freely accessible to other threads. So I built a custom data structure for this. It has two arrays, one for the stored indices and one for the per cell objects count. When reading from or writing to a cell, the structure logs only the memory chunks belonging to that specific cell, both the map array section and the count entry. To sum it up, here I have a spreadsheet with memory and performance estimate. Here we have limits. How many cells there are in a system, what is the entities cap, how many entities can be in one cell, how many cells one entity can take. Physics body array size is entities cap. Each element take that much memory. Map array is a 4D array built with 3 spatial dimension and that many entities in one cell. Each element is a uint, index of an entity. Cell count is count of how many entities in each cell during the execution. Its size is just an amount of cells. Add to map operation is adding each object to the array. Its complexity is total number of entities multiplied by cell cap per entity. As you can see now, add to map is the most complex operation. It might take up to 40 millions of operations if your limits are high. That's it for today. In the next video, I'm going to talk about the intersection and collisions calculations. If you have any questions about the system so far, please let me know in the comments. Also, don't forget to hit the like button and subscribe to this channel. And I'm going to see you in the next video.